Hello future engineers, welcome to my YouTube channel. So for my subscribers and for those who are new here, please inspire me by sharing my videos to your friends and to your friends' friends so that I will be more inspired to do more lecture videos and sample problems related to engineering subjects, especially civil engineering. And that's the only way I'll be inspired more to do lecture videos and sample problem videos. This work is very, very tiring and I need to be refreshed and I need to be energized by your support through sharing my videos. So please do so. So here we go. This is a very challenging problem. So for this case, we will select C as our moment center. So we need to compute for the reactions. So summation moment about D equals 0. So we have AY times 11, then minus 0.5 of 3 times 30. Then this is 1. 1 plus 4 is 5. That's the moment arm for this triangle here. And minus 0.5 of 4 times 18, where 18 is 30 minus 12. We divide this loading into triangle and this loading here into rectangular loading. So 0.5 of 4 times 18, the moment arm is 2/3 of 4. That's why you have 8/3. And finally, for the 12 kilonewton load, 12 times 7, this is 7. Then half of 7 is 3.5. There is already 3 here, so the centroid is 0.5 meter from the, so that's why you have 0.5 there. So therefore, computing for AY is equal to 33 kilonewtons. Then summation forces Y equals 0 to solve for RD. So we have 33 plus RD plus, we just copy this, minus these areas, remove the moment arms. So minus 0.5 times 3 times 30, minus 0.5 times 4 times 18, and minus 12 times 7. So R sub D is equal to 132 kilonewtons. So let's show the reactions. And since we select C as our moment center, let's now prepare the moment diagram by parts. So first we have 33 times 7. That's 231 over EI. Moment due to this triangular loading is 0.5 times 3 times 30 times 1. For 132 kilonewtons. 132 times 4 is 528 over EI. Then for this triangular loading, third degree, first degree plus 2. So 0.5 or 1/2 of 3 times 30 times 1. Third degree, that's 45 over EI. Then for this rectangular loading, let's divide it into that manner. So I replace this uniform loading into concentrated load and moment, because if we proceed directly to this C here, then the area beyond D will be a little bit difficult to compute, especially the centroid. We need to compute the slope also. So let's replace this. Let's do the moment diagram. Let's cut it here. 12 times 3 is 36 kilonewtons. Then the moment 12 times 3 times 1.5 is 54. So as shown in the figure, we have 54 kilonewton meter here. This is second degree. Then this 36 kilonewton, this 54 over EI or moment will be transmitted to C as shown. Then we have still moment of 36 times 4 which is equal to, the height is 144, but the total moment at C is 54 plus supposedly 144. So it's like 12 times 3 times 5.5. That should be 54 plus 144. But anyway, it is already shown here. So that's the technique if you evade from constructing moment diagram by parts, which will make the area difficult to deal with. So that's the technique. You have to do it this way so that these areas will be easy to compute and the centroids are readily known. So next, take note that we haven't yet included this and this triangular loading. So for this loading here, second degree, we have 36 times 4 times 2, second degree. 36 times 4 times 2 is, the height is 96 over EI. 36, oh sorry, not 36, but 12 times 4, 48 times 2, so 96 over EI, that's the height. Then for this triangle here, it is 1/2 or 0.5 of 4 times 18 times 4 thirds. And the curve, the diagram is third degree. So again, 1/2 or 0.5 of 4, so that's 2 times 18, 36 times 4 thirds, 48. The height is 48 over EI. So this is the complete moment diagram by parts. There are so many areas involved. But anyway, dealing with this moment diagram can help you develop your skills in area moment theorems. So EI theta AC is the area between A and C. So 0.5 of 7 times 231. Then minus 1/4. The area is 1/4 or 0.25 of 3 times 45. So theta AC can now be computed, the angle formed between the tangent at A and the tangent at C. So it is 774.75 over EI. So next, let's compute EI deviation of D relative to the tangent at A so that we can compute the slope at A. So it is the moment of areas between A and D with respect to D. So beginning with this area here, 0.5 of 7 times 231. This distance from C, centroidal distance of triangle from C is 7 thirds. Then since our moment center is D, we sum up moment about D. So the moment arm is 7 thirds plus 4. Plus 4. Then for this area here, 0.5 of 4 times 5 to 8. And 2 thirds of 4 is 8 thirds. Distance of centroid from D is 8 thirds. Then for this area, minus 1/4 or 0.25 of 3 times 45. This distance is 3 over degree plus 2. So 3 over 3 plus 2 is 3/5, 0.6. 0.6 plus 4. So that's why you have 4.6 here. Then minus this moment of this rectangle, 4 times 54 times 2. So 2 minus this moment of this, of the area of this triangle, minus 0.5 of 4 times 144. The moment arm is 2 thirds of 4 or 8 thirds. Then minus the moment of this area with respect to D, minus 1/3 of 4 times 96 times, because this is 4 over 4, 1. So it's the distance of its centroid from D is 3. 4 minus 1. Again, this is 4 over 4. 4 over 2, degree 2 plus 2, so 1. So its distance from the right is 3. Finally, the distance of the centroid of this third degree curve is from the leg is 4 over 3 plus 2, 0.8. So its distance from the right is 4 minus 0.8 3.2. So minus 1/4 or 0.25 of 4 times 48 times 3.2. So using your calculator there, deviation of D relative to the tangent at A can now be computed, and it is 6043.65 over EI. So let's do the tangent at A. Because this is positive, meaning D is above the reference tangent as shown in the figure. So this is deviation of D relative to the tangent at A, and this is the slope at A, theta A, which is negative because it is sloping downward. Therefore, theta A is negative deviation of D relative to the tangent at A divided by 11. So it is negative 549.423 over EI in decimal. Then the elastic curve, approximate elastic curve, so that we can analyze the slope and deflection at C. So this is deviation of C relative to the tangent at A. That's the point C on the elastic curve. This is the tangent at C. Because EI theta EC, the value is 774.75, which is greater than theta A. So meaning to say it extends above the horizontal, because from the tangent at A to the horizontal, that's theta A. Then from the tangent to the tangent at A to tangent at C, that's theta AC, which is greater than theta A. So meaning to say theta C from the horizontal would be positive. So that's the horizontal line. This is theta A. And that angle to the tangent at C is theta AC. And the angle between the horizontal and the tangent at C is theta C, this angle here. So theta C from the figure is positive absolute value of theta AC minus absolute value of theta A. So this is theta C. So absolute value of theta AC, 774.75. It is positive minus absolute value of theta A, which is this. So theta C can now be computed. It is equal to 225.327 over EI. Next is we compute this deviation of C relative to the tangent at A. So that's just moment of area between A and C with respect to C. So there are only two areas. We can easily compute that. And therefore, this is deflection at C, which is negative below the horizontal x-axis. The total distance from the point on the horizontal beam to the reference tangent at A, because this distance is 7 and this is theta A, the whole distance here is 7 theta A. So that delta C is negative of absolute value of 7 theta A minus absolute value of deviation of C relative to the tangent at A. So let's compute first EI deviation of C relative to the tangent at A. Area 0.5 of 7 times 231. Then distance of centroid of area from C is 7/3 minus this area here, moment of this area, which is 1/4 or 0.25 of 3 times 45. Moment arm is 3 over 5. 3 over 5, 3 over 3rd degree plus 2, 3/5 is 0.6. So deviation of C relative to the tangent at A is equal to 1866.25 over EI. Finally, we can compute delta C. So delta C is equal to negative of 7 theta A, absolute value of 7 theta A, minus absolute value of deviation of C relative to the tangent at A, which is 1866.25 over EI. So delta C can now be computed, negative 1979.711. Negative 1979.711 over EI. Next, we need the slope at D to analyze E as well as G. So to do that, let's compute EI theta CD, because we already know theta C. So that's the area between C and D, this area here. So beginning with this positive area, 0.5 of 4 times 5 to 8 then minus 4 times 54, minus 1/2 or 0.5 of 4 times 144, then minus this area here, which is 1/3 of 4 times 96, then minus this area here, which is 1/4 or 0.25 of 4 times 48. So theta CD using your calculator is equal to 376 over EI. So that's the angle formed between the tangent at C to tangent at D. Since this is positive, so it means counterclockwise rotation from C to D. So this is the tangent at D. Then this angle between them is theta CD. That's theta CD. So theta D, therefore, which is the angle that the tangent at D makes with the horizontal, because this is the horizontal to tangent at C is theta C, then plus theta CD, that's the theta D. Again, horizontal line to the tangent at C, that's theta C, then plus theta CD, then that's the angle that the tangent at D makes with horizontal. Therefore, theta D is theta C plus theta CD, and it is sloping up to the right, so it is positive. So absolute value of theta C plus absolute value of theta CD, that's theta D. So absolute value of theta C, 225.327 over EI, plus absolute value of theta CD, which is 376 over EI. So theta D is equal to 601.327 over EI. So next, let's compute EI theta DE. So it is this area here, negative 1/2, negative 1/3 second degree of 3 times 54. So it is negative 54 over EI. So meaning to say, from the tangent at D to tangent at D, the rotation is clockwise because that's negative. So EI, division of E relative to the tangent at E, is area. We just add the moment arm. So this distance is 3 over 4 or 0.75 because this is second degree. Distance from centroid to vertical leg is 3 over 4, 0.75. So its distance from E, because division of E relative to D is 3 minus 0.75. That's why we have 2.25. So it is equal to negative 121.5 over EI. So in the next slide, we copy these values because we need to analyze E. And it is already the figure here is complicated that I cannot present the details. So let's have it on the next slides. So here we go. So remember, this is the tangent at D, theta D. That's also theta D. And we now consider point E before G. So this is the tangent at E, and this angle is theta DE, which is already computed in the preceding slides. And the angle that the tangent at E makes with the horizontal is theta E. That's theta E. The angle that the tangent at D to the horizontal, this total angle here, is theta D. So if we analyze, theta E is absolute, theta E is positive because it is sloping up to the right. It is theta D minus theta DE. Again, the angle that the tangent at D makes with the horizontal is theta D. Then since the angle formed between the tangent at D to E is theta DE, so theta E, if you analyze it, is theta D to the horizontal minus theta D, and it is positive. So these are the values. Theta D is 601.327 over EI. Then theta DE is negative 54 over EI. And deviation of E relative to D is negative 1 to 1.5 over EI. So theta E is absolute value of theta D minus absolute value of theta D. So therefore, theta E can now be computed. It is equal to 547.327 over EI. Then this is deviation of E relative to the tangent at D, negative. So meaning to say, point E on the elastic curve is below the reference tangent as shown. So that's deviation of E relative to the tangent at D, which is already computed. Then this is delta E, which is above the x-axis. So it is positive. The total vertical height of this right triangle is 3 times theta D. So therefore, delta E is positive of 3 times, absolute value of 3 times theta D, this total vertical height, minus absolute value of deviation of E relative to D. So we subtract this white vertical distance. So delta E is equal to absolute value of 3 times theta D, this is theta D, minus absolute value of deviation of E relative to D, which is negative 1 to 1.5 over EI. So delta E is equal to 1682.481 over EI. So finally, we analyze G, and G is 8 meters from A, so 1 meter from C, 3 meters from D. So since we consider this portion only, G to the right, because if we consider CG, it's very complicated, especially the areas. So this is 18, and since the distance of G from D is 3 meters, so 3/4 of 18, that's the intensity of the load at G here for the triangular part. So this is 12 kilonewton per meter. Then this is 3/4 of 18. This one, this yellow intensity. So 3/4 of 18 is 13.5 kilonewton per meter. So therefore, this is 528. So we project it here. The value here is 3/4 of 528, and that is 396. So this remains 54. This one is 3/4 of 144, 108 over EI. For this value, because this is second degree, so we compute the moment of this triangular loading with respect to G. So first, for the second degree part, it is 12 times 3 times 1.5. 12 or 3 times 12, moment arm 1.5. So that's 54, because 3 times 12 is 36 times moment arm 1.5. So 54 over EI. Finally, for this triangle, 0.5 of 3 times 13.5, moment arm is 1, 1/3 of 3 is 1. So it's just 0.5 times 3 times 13.5. So that's 20.25 over EI. So we need to compute deviation of G relative to the tangent at D. EI deviation of G relative to the tangent at D is, let's consider these areas here. So 0.5 of 3 times 396. Then we compute the distance of the centroid from G. So that's 1. For this area, minus 3 times 54 times 1.5. For this area, minus 0.5 times 3 times 108 times 1, because 1/3 of 3 is 1. And for this second degree, minus 1/3 of 3 times 54 times 3 over 4, or 0.75. 3 over 4 is 0.75 for the second degree curve. Distance of its centroid of this portion to this vertical distance, vertical leg, that is colored dust black. So 3 over 4 is 0.75. Finally, minus 1/4 of 3 times 20.25. So minus 0.25 of 3 times 20.25, then 3 fifths. 3 fifths is 3 over third degree plus 2, so 3 fifths of, 3 meters over 5, so zero point 0.6. Using your calculator there, deviation of G relative to D is equal to positive 139.3875 over EI. So that means point G on the elastic curve is above the reference tangent at D, as shown in the figure. So this is deviation of G relative to the tangent at D. So that's why it's positive. Point G is above the reference tangent. Then this is delta G. That's delta G. Then the slope at G. So EI theta GD is simply the area between G and D. So we copy these areas here that we computed. We just remove the moment arms. So minus 3 times 54 minus 0.5 times 3 times 108. Then minus 1/3 of 3 times 54. Then minus 0.25 times 3 times 20.25. So using your calculator, theta GD is 200.8125 over EI. Positive means from the tangent at G to the tangent at D, it is counterclockwise. So this is the tangent at G, this is the tangent at D. So this is the angle between the tangent at G and the tangent at G counterclockwise is theta GD. This is theta GD. That one. So the angle that the tangent at G makes with horizontal is theta G. So this is the horizontal. This is theta D, the angle that the tangent at D makes with the horizontal. Then the angle that the tangent at G makes with the horizontal is theta G also. So this is theta G. Theta D, theta, that's theta D, angle between the horizontal and the tangent at D. This is the tangent at G, and this is the horizontal. So this is theta G, the yellow. So the total angle, theta G plus theta GD, is the angle that the tangent at D makes with horizontal. So in other words, this is theta D. Slope of the tangent at G is positive because it is inclined up. So therefore, theta G is theta D, absolute value of theta D minus absolute value of theta GD. So theta G is absolute value of theta D, which is 601.327 over EI minus absolute value of theta GD, 200.8125. So theta G can now be computed, and it is equal to 400.515 over EI. So you compare that with our answers in example 100M. They are equal. Then finally, for the deflection at G, this total distance, delta G plus deviation of G relative to D, is 3 meters times theta D. So therefore, delta G is negative of absolute value of 3 theta D minus absolute value of deviation of G relative to D. So you just look at the figure. This is again 3 times theta D. So delta G is negative of quantity 3 times theta D minus absolute value of deviation of G relative to D, which is 139.3875. So finally, we can compute delta G, negative 1664.594 over EI. So that's it. It's very tedious and long, but I hope you were able to follow and understand the solution, because if you were able to patiently listen to the explanation and the discussion and you were able to follow, then that means you are prepared for the usual problems in deflections. This is extraordinary, and your instructors cannot think of this definitely. Uh, Deflection problems will just be simpler than this problem, definitely. But if you were able to follow the solutions, then you are highly prepared for an exam or for your test.